Hi, this lesson is on the limit laws. So there are 6 laws here that can be used to evaluate limits. And so first we suppose that C is a constant and that you have a limit as x approaches a of f of x and a limit as x approaches a of g of x that both exist. Then the following laws would be true. The first law and the second law are very similar. So what they're saying is, in the first one, it says if you take the limit of the sum of two functions, that is equal to the sum of the limits. And the second one says that if you take the limit of the difference of two functions, that is the same as taking the difference of the limits. So sometimes evaluating it the way they are on the right makes sense, and sometimes we evaluate it the way it is on the left. The third one is used really frequently. It says that the limit as x approaches a of c times f of x is the same as c times the limit of f of x. So you can just evaluate the limit and then multiply by the constant. Sometimes that does make calculations easier. Numbers are smaller. The fourth one says that the limit of a product is the same as the product of the limits. That one is called the product law. The fifth one is regarding a quotient. So it says that the limit of f of x over g of x is the same as the limit of f of x divided by the limit of g of x, as long as the limit of g of x is not equal to 0, because remember, division by 0 is undefined. The sixth one has two parts to it that are similar. The first part says that if you take the limit of f of x to the nth power, that is the same as taking the limit of f of x and then raising it to the nth power. That one is especially helpful because once you evaluate a limit, you typically have a number, and then raising a number to an exponent is definitely less work than expanding a function to a power. So if just imagine even something simple like a binomial, and you had it raised, let's say, to the 8th power. So expanding this to the 8th power would take a bit of time versus just evaluating the function and then raising the number to the 8th power. That would be an easier operation. And the second part of the sixth law is very similar, says that the limit of the nth root of f of x is equivalent to the limit of f of x and then take the nth root. Again, the way it is written on the left side is a lot more work algebraically. It's much easier to take the nth root of a number, which is what you would have once you evaluate the limit. So we're going to apply some of these laws to evaluate the examples in this first example here, and there's more than one part. So you're given that the limit as x approaches 3 of f of x is 4, the limit as x approaches 3 of g of x is negative 2, and the limit as x approaches 3 of h of x is equal to 0, and we'll use the limit laws to evaluate each of the following limits. So the first example is asking you to evaluate the limit as x approaches 3 of 5 times the square root of f of x divided by 3 times the square root of g of x. So we're actually going to use 3 laws here. The one for a constant in front of a function, the one for a quotient, and the one for a square root, because we have all 3 situations here. So first I'm going to rewrite this using the limit laws, and this is equivalent to 5 times the square root of the limit of f of x divided by 3 times the limit of g of x. So instead of just having one limit on the outside like we had in the original problem, I now have a limit inside of the radical and a limit inside in the denominator after the coefficient of 3. So now I can plug in what I know. We know what this limit is. It's equal to 4, so that becomes a 4. And this limit is negative 2, so this denominator becomes 3 times negative 2. And when you simplify the results, your numerator is 10, your denominator is negative 6, which reduces by a factor of 2 to negative 5/3. Okay, now we move on to part B, and part B is asking you to evaluate the limit as x approaches 3 of negative 2 h of x minus g of x to the third power. So I'm using law number 2 because of the difference, law number 3 because of the coefficient in front of h of x, and law number 6 because of this exponent associated with the g of x. So first I rewrite it in terms of the limit laws, applying the laws that I just checked off. So this will be negative 2 times the limit as x approaches 3 of h of x minus the limit of g of x raised to the third power. So we know what the limit of h of x is. It's 0, so I plug that in here. Once you're plugging in what the value of the limit is, you should no longer have any limit notation on this line here. And then you plug in what the limit of g of x is, which is negative 2. And so I have negative 2 to the third power. That leaves you with 0 minus negative 8, which becomes positive 8 as your limit value. Okay, so that was 2 examples of how we used several limit laws in order to evaluate this limit. So here we're going to use the limit laws and the given graph to evaluate each of the following. So we want to evaluate the limit as x approaches 0 from the right of 4 times f of x minus 2 times g of x. So I will be using 2 limit laws, the one for a coefficient, because each of these functions have a coefficient, and the one for a difference, because we're subtracting. But this time, the limits are not provided to you. We have to read the graph. So if I read the graph of f of x, that's the one in blue, as I get closer and closer to 0 on the right side of 0, and I follow the path of this, it looks like it's going towards that value. So and on this line, all I did was rewrite it in terms of the limit laws, but then from here to the next line, I've evaluated it. The limit as x approaches 0 of f of x is equal to negative 2. But now I also have to evaluate the limit of g of x as I get closer and closer to 0. You can see that g of x is a constant, and the closer I get to x equal to 0 on the right, the value of the y gets closer and closer to negative 3. So I'm left with 4 times negative 2, which is negative 8, minus 2 times negative 3, which becomes plus 6, and negative 8 plus 6 gives me a limit value of negative 2. Okay, so we talked about how to read graphs to evaluate limits in the previous section in 13.1, if you need to review some of those before you continue. Here we'll be using the same graph, but this time I want to evaluate the limit as x approaches 2 of the square root of 3 times f of x divided by negative 2 times g of x. So again, I'm using several limit laws here. One for the radical, one for the coefficients in front of f of x and g of x, and the law regarding a quotient. So when I rewrite this in terms of the limit laws, it should look like this. Root 3 is now a coefficient. So it's root 3 times the square root of the limit as x approaches 2 of f of x divided by negative 2 times the limit as x approaches 2 of g of x. The limit of f of x, if you read the graph, whether you're approaching f of x from the left or the right, you follow the path, you're getting closer and closer to that value, which has a value of 4. So this becomes root 3 times root 4. And as I get closer and closer to 2 on the graph of g of x, well, it's a constant, so it's still going to be negative 3. So this becomes 2 root 3 divided by positive 6. The 2 and the 6 cancel, so I'm left with root 3 over 3 as my limit value. Okay, So there are other algebraic techniques other than just factoring, which we did again in the previous lesson. So we'll practice the factoring again, but then we'll also use some other techniques in order to evaluate a limit through algebraic methods. So in this example, I have the limit as x approaches -1 of x to the fourth minus 1 over x plus 1. Again, I can't just plug in -1 because if I do, I'll be dividing by 0. But this numerator is factorable, factors into x squared plus 1 and x squared minus 1. This factors even more because the x squared minus 1 is the difference of perfect squares. So the x plus 1 in the numerator and the x plus 1 in the denominator will cancel out. Once I cancel that factor out, I am able to substitute the -1 into the part that's left, which is this. And so once you apply direct substitution, you no longer write the limit in front of the expression. You just plug in the number. And that works out to be 2 times -2, which gives me a limit value of -4. So although the function is not defined at -1, as you get closer and closer to -1 on the left or on the right side of the graph of this function, your y value is getting closer and closer to -4. So again, if you recall an earlier lesson, when I talked about this, that means that this graph has a hole at -1, -4. You can plug this into a graphing calculator and zoom in on -1, -4, and you should see an open circle there. Not all graphing calculators will show that to you, but some graphing calculator apps will definitely show it as an open circle. Okay, next example, we have a radical. So I have the limit as h approaches 0 of the square root of 25 plus h minus 5 all over h. Again, I can't just plug in the 0 because I'll be dividing by 0, and we know that is undefined. So I'm going to use a technique that's typically taught in algebra, which is to simplify a radical expression where you have a numerator and a denominator. You can use the concept of conjugates. A conjugate means that we're going to multiply by the same expression except the opposite sign in the middle in both the numerator and the denominator. And when I do that, I have to FOIL out the numerator. And so the first term, the square root of 25 plus h times itself, will just be 25 plus h. And then I didn't write it out because your outer and inner terms basically cancel each other out because they are the same but with opposite signs. So that's your outer term, that's your inner. They cancel out, so I didn't write it. And then the next number that you see on the next line is -5 times 5, which is -25. And the denominator, I just put them next to each other. Don't distribute the h. That doesn't really help. So you want to just leave them as a product. So now in the numerator, you can see that the 25s will cancel. So my numerator is just h, and my denominator is h times the square root of 25 plus h plus 5. Then the h's will cancel. And at that point, you're left with the expression on the next line. And that's where you can now see that I can just plug in the 0 in for h and get a number. So when I do, you end up with 1 over 5 plus 5 because the square root of 25 is 5, which gives me an answer of 1 over 10. So this limit is equal to 1/10. Okay, here's another one. We have the limit as x approaches 1 of 2 over x minus 2 over x minus 1. Again, I can't just plug in the 1 here. I'll be dividing by 0, so we have to use a different method to simplify the expression. So there is more than one way to do this. So what I decided to do was I wrote this as a single expression because they both, I wrote this as a single expression by getting a common denominator for the second term. So I multiplied the 2 by x over x, so the 2 becomes 2x over x. And then on the next line, that numerator is written as a single fraction with a common denominator. And this division symbol right here is the same as multiplying by the reciprocal of the denominator. So I did a couple things on this second line. I wrote the numerator as just one fraction, and instead of writing divided by x minus 1, I wrote times 1 over x minus 1. But that numerator here factors. It has a common factor of 2. And I just wrote these two next to each other. Again, don't multiply them out. That doesn't help. And then you can see that my numerator and the denominator have a factor that looks similar, but they aren't quite the same. And in order for them to be the same so that I can cancel them, I have to factor out a -1 from the numerator. So the 2 turns into a -2, and the 1 minus x turns into x minus 1. And then at that point, I can cancel the x minus 1s. So you're just left with the limit as x approaches 1 of -2 over x. And this does allow you to plug in the 1. And so your limit value is equal to -2. Okay, so here's one for you to try. So you're given a graph and you're asked to evaluate the following limits based on what you read off of the graph. So this one is asking you to evaluate the limit as x approaches -4. We'll do the first one together. The closer you get to -4 on the left side or the right side, if you follow the path of the graph, it is getting closer and closer to the y value of 2. So the answer for that limit is 2. Remember, the function doesn't have to be defined in order for the limit to exist. For part B, you're asked what is the value of f of -4. Since there is no line or solid point associated with x equal to -4, you would just say that this one is undefined. So the limit exists, but the function does not. For parts C and D, you have to take the limit as x approaches 1, but this one is from the left side of 1, and this one is from the right side of 1. And then evaluate f of 1. For part F, you want to evaluate the limit as x approaches 6. That means you have to check from the left and the right side. Then evaluate f of 6. And then there's a question. Which of the following limits do not exist? The limit as x approaches -4, which we have already established it does exist. The limit as x approaches 1, you really have to answer this question, these two questions first. And the limit as x approaches 6. So you have to answer part F in order to answer the last part of H. So that's it for this lesson. Good luck.